Welcome to part 2. This is the 1.2 lesson video. We're going to be talking about intervals where functions are increasing, decreasing, and constant. So we're going to start off with increasing intervals here. And each of these are going to have kind of a technical definition where we base it on the inputs and the outputs of the function, and another more sort of intuitive definition where we just sort of describe it. So a function is increasing on an interval if for any x1 and x2, so any 2x values in the interval where x1 is less than x2, so x1 is on the left of f2, that's the way those values would work, then the output for x1 is less than the output for x2. Okay, so let's first start off by kind of thinking about this a little bit more intuitively. When we say that a function is increasing, we mean that it's going up, right? In general, when we talk about graphs increasing or decreasing, we're referencing what's happening as we move from the left to the right. So if we examine this graph down here, you can see that this function is increasing from approximately here to here, right? In this gap, this is where it is increasing, right? We start down low, we're moving to the left, and we're going up. Right? So in general, this function is decreasing, then increasing, then decreasing again. But really all we're worried about here is this one increasing interval. When we talk about the interval, we're splitting up the domain of our graph. So we have this here. I'm going to move that over real quick. So we're increasing in this interval that I'm going to kind of outline from there to here. This is our interval where the graph, the function is increasing. Obviously, at the endpoints, it's no longer increasing. It's kind of switching over, so we won't include those. And this technical definition, what it's saying is, well, let's just pick two values in here. So for any two values, x1, x2, where x1 is less than x2, so that means that it's on the left, right? If a value is less, if we're talking about on a number line, it'll be to the left. Then the output of that function, which would be right here, approximately, this location, f of x1. So that's our output, at least approximately, is going to be less than the output for f2. And that's true, right? The output for f2 would be approximately over here, of x2 would be approximately over here. That's going to be true for any 2 points that we choose inside of this interval, right? That's a really technical way for us to write the definition. I don't need us to necessarily understand that, though. It will be helpful when you do learn things like the intermediate value theorem, for instance, in calculus, or some other things like that. It is important to kind of understand these technical definitions when you move into calculus. For us, it's going to be enough or sufficient at this point just to talk about how the graph is going up, right? As we move from the left to the right, the graph is moving in an upward fashion, only upward. So we have increasing intervals. We also have decreasing intervals, right? So we can look at this graph, right? We can say that it's decreasing, decreasing starting right up there at that. I have really gone too far, so let me fix that by going further. Let's go back here. Okay, so we have a decreasing interval that starts right up here at the vertex of what looks like a parabola here. And for us, it kind of looks like it keeps going. It doesn't actually stop decreasing. We're going to probably assume that it keeps going on this downward trajectory forever. Again, same technical definition, slightly different, right? If we pick any two values in this decreasing interval, then let's just pick some random ones, so here and here. If it's decreasing, then we have our x1 and our x2. What's important to know, right? Really technical, if it's decreasing, then the output for x1, so f of x1, is actually going to be greater. It's going to be higher than the output for f of x2, right? That's a really technical way, again, to define this. Using these sort of inequality relationships. So the output at x1 is going to be greater than the output at x2 if it's a decreasing on that interval. And so that, again, that's a really technical way to write it. For our cases, right, as we're moving left to the right, from the left to the right, it's going down. Okay. And then finally, this is not going to be particularly common, but some functions may have constant intervals. Constant needs to be perfectly flat, can't be going up or down at all, has to be perfectly flat. And so when you pick two values in that interval, so from here to here, we can see that the graph's perfectly flat. When we pick two values in that interval, any two values in x1 and then x2, then the outputs at both of those spots have to be equal. F of x1 would be equal to f of x2, right? And so both of those would be right here, be f of x1 and f of x2. They'd have the same output. That's what it means to be constant, right? It's not moving up or down, the outputs are staying the same. All right, let's go ahead and take a look and apply this and talk about where a graph is increasing, decreasing, or constant. So here we have a graph, kind of looks like a cubic graph, third degree polynomial. We want to talk about the intervals where this graph is increasing, decreasing, and constant. So I'm going to draw some vertical lines here. Basically, we can kind of section this graph into three distinct intervals. So we have one here. If we draw some lines here through these values, right? So we have this first interval from -∞ all the way to -1. That's this left side of this graph. So here to here, from, let's use an arrow. So from here all the way over to -1. We always talk about our intervals as values along the x-axis, intervals of our domain. So we're talking about from -∞ all the way to -1. What's happening with our graph? It's decreasing, right? It's decreasing until it hits this particular point, and then it's changing. So we have a decreasing interval from -∞ all the way to -1. For these types of intervals, we never include the endpoints because once we reach this endpoint here, it's no longer decreasing. It actually stops. And it would be moving far. Now we would be moving onto a different interval where it's actually increasing. So we just use parentheses to not include that. Well, then what's happening? So now in between these two blue lines here, our graph is no longer decreasing, it's actually increasing. So it's increasing from -1 to 1, -1 to 1. That is actually the only increasing interval. And then we reach this point here again at 1, and the graph is decreasing again. So we actually have another decreasing interval. So we're going to give this union symbol from 1 to infinity, right? Again, we're going to assume that this graph, as we keep moving on to the right here, it is actually decreasing forever. And, as we move to the right forever, we are approaching infinity. So those are going to be our intervals. And there is no interval where this graph is constant, because this is, a polynomial function. It's going to be up and down. It's not going to be constant anymore. Okay, let's go ahead and move forward. Here we have a parabola, a quadratic. We're going to talk about what's going on with this graph. I'm going to use some arrows here so we can see that it's increasing, then it's decreasing. Remember, we're always reading this graph from the left to the right, so we want to follow that. It's going up, 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 up. It hits a maximum value, down, 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 forever. So we just have two distinct intervals here. So we have an increasing interval followed by a decreasing interval. And that break happens right here at -3. Again, we're talking about the x values. That's how we establish this. So from -∞ all the way over to -3, we're increasing. So that's going to be our increasing interval. And that's the only one that's only increasing there. And then it's decreasing. So from -3 all the way to infinity, to the right forever, it's going to be decreasing. Again, this is a polynomial function, a quadratic. It's not going to be constant anywhere. It's never going to be flat. So there's going to be no or none constant intervals. Okay. Let's go ahead and clear this and move forward. All right, here we go. Here we have what looks to be a piecewise function, and notice now we have at least a constant interval this time. We haven't had that yet to this point. So as we're following this graph along, right, it's increasing, 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 then it's constant, and then it's decreasing, right? Again, we're following it from left to right. So pretty simple. We're increasing, we're constant, we're decreasing. Again, we can kind of split this up along the x-axis and figure out where sort of these breaks are. So here are breaks at -1 and at +3. So let's go ahead and write out these intervals. Again, we're increasing from -infinity all the way over to right here, this line at -1. We are now constant between -1 and 3. So constant between -1 and 3. And then we're decreasing from 3, starting at 3, all the way to +infinity forever. So again, because it runs off the graph, we do have to assume that it keeps kind of following that graph all the way to the right or the left. Alrighty, let's go ahead and clear this. And that's actually going to be all for part 1. So I'll see you guys in part 3, where we look at extreme points.